you can't divide it down any further. So if you look at it and there's one of those compounds where you have one atom, then that's the smallest ratio. So this is okay. Yeah, that is an empirical formula. That's fine. How about H2O2? No. Hydroperoxides, empirical formula is HO. Right? That is divisible by 2, and so that's the empirical formula for hydrogen peroxide. So if I found the empirical formula for hydrogen peroxide, I guess my ratio is going to be 1 to 1. It's not going to come out 2 to 2. If I do a calculation and I find the empirical formula, which you're going to do here in a second, you're not going to come up with a ratio of 2 to 2. It's going to be 1 to 1. It's going to be the same number of moles of both. Yes?
So it doesn't matter like what element it is, like what charge it has?
Nope. Nope, it has nothing to do with charges. It's how the ratio is working. How about glucose? This is glucose. Is that the simplest ratio for glucose?
No.
No, what's the simplest?
6.
C?
H6, H2O.
Oh.
What?
Okay, they're all divisible by 6, right? The smallest ratio is 1 and 2 to 1.
Oh, so I was dividing by 6 too.
So glucose, when I would find the empirical formula, when I do this calculation that you guys are going to do here in a little bit, you're going to come up with a ratio that's 1 to 2 to 1. It's going to give you 1 mole of carbon, 2 moles of hydrogen, and 1 mole of oxygen. So if I was doing an experiment where I could find the weight of carbon, hydrogen, oxygen, and glucose, and I find them, and then I convert them to moles, this is the ratio I'll get. It's not that ratio. Now, I can get that ratio later on, and I'll share that probably maybe Wednesday of next week. Okay? Where you can find the empirical formula, or what we call the molecular formula. Now, what about the last one? Is that the empirical formula for that one? Yeah. Because what you have is you have 2 lead, you have 3 sulfur, and you got 12 oxygens. You can't divide them down any further. Okay? None of them are divisible by the same number. So, questions on empirical formulas. I'm just telling you what it is, what it represents. It does not necessarily represent the actual formula of the compound. Okay? Many times it does, but there's times that it doesn't. Especially organic compounds like carbons and hydrogen and oxygens hooked together. Okay? It doesn't. So what I'm going to do is we're going to look at, I'm doing a problem where I'm going to give you the percentages. And then with those percentages, we're going to go ahead and find the actual formula. And so it's called finding empirical formula is what it's called. This is really, to me, this is what I like about chemistry. Up to this point, I mean, I don't mind doing the things that we've done. A lot of it is prep work, so we can do things like this. And this is called Quantitative Analysis. Now, they've got machines that do this. Okay, they got what's called a gas chromatograph. Okay, if you go down to the state crime lab in Nebraska, they've got rows and rows of these. And they take a drug like meth, they dissolve it in a solvent, usually methanol, okay, methanol, or ethanol. They dissolve it, they have to dissolve it, and they put it into this copper tube, and they heat the copper tube up, and it gets into a gas, and then that gas moves along, and there's portions of that molecule, depending upon how long it takes to get through that tube to the other end, the time-wise, they can determine what the mass is of that compound. They can determine the mass of that compound. They know that the compound meth has this weight. Then it comes out on a graph as that weight. Now there's other impurities in that, because if it's meth and somebody's home cooking it, it's not going to be pure. So there's going to be other things in it. But they'll see that peak right where meth is, because they have pure samples of meth that they run through it as a test, as a control. And they go, all right, they give this to the lawyer, or they give this to to the prosecutor and they say, here's the deal, it's meth, okay? And so they'll prosecute them based upon whatever the law is, okay, and whatever the circumstances are. We're kind of doing that here, but we're taking the weights and finding the empirical formula. So it's kind of neat. We can take lab data and we can come up with an actual formula of how the atoms go together. We get an actual picture of how the atoms go together. So here's 3 percentages you need to write down. If you want to keep them a little bit of distance apart so you can do some calculations with them, that's probably a good deal. So 36.48% of this compound is made up of sodium. That's how, so about 1/3 of its weight is sodium by atoms. 25.41% is sulfur. Okay? And 38.02% is made up of oxygen. Okay, the very first thing you do is, if you add these all up, you get 100%. So there's nothing else, there's nothing missing. Okay, we got everything. There's nothing else in there other than these 3 elements. Okay? So this is what I'm going to do. I'm going to say that instead of 100%, I have 100 grams of this compound. So can you tell me how many grams would be oxygen of this? So I've got this compound in a 38 grams. Oh, good. I don't have to go any further. 38 grams would be oxygen, right? And 25.4 grams, for 1, try to get that in there, sulfur. And then 36.48 grams sodium. So we just say, hey, we got a 100-gram sample. Wow, that's pretty easy. Now we got grams. Guess what we can do now? We got grams. What can we do? Find moles. If we know moles, then we can do a comparison of moles and get the ratio. So the next step for you to do is to change grams to moles for each of those elements. So how would we go about changing sodium grams to moles? What would we do? Where would we have to go? Yeah, find out what 1 mole is and then convert it. So what's 1 mole of sodium equal to in weight? 22.98, right? Well, actually, okay, 99. Okay, so go ahead and convert all of those into moles. Okay? Go ahead and convert all of those masses up there into moles. I'm going to take them out 3 or 4 digits. The more digits I take it out up to a point. Okay, you can't use any more than you're supposed to. So all 3 of those we're going to have 4 digits. Okay, if we go by the rules of significant digits. So this first one would be 1.587.
Why are you going 3 places?
4 places because of those 4 numbers.
Okay.
If you limit yourself on these guys, you're going to mess yourself up and you're going to get problems wrong where you shouldn't get them wrong. Because you're not taking the time in which to take it out far enough, and it'll mess you up when you come up with a formula. I've seen it, and I'd love to give it right, because everything's done right. You're just limiting your answers too much. And I'll see it, because some of you will just kind of do what you want, and maybe put 1 or 2 digits down, and that will mess you up on this next part. So don't. Like on this one, somebody might put 1.6, and some of you put 0.8 on that one and 2.4. That could mess you up.
Why did yesterday we do that? We only went 2 decimals.
Wouldn't it be 0.7925?
I got, well, you might have went 32.067. I used 32.07. Okay, yesterday, what do you mean yesterday we only went
Like
2 places?
yesterday we only went after the decimal 2 places.
Oh, yeah, but we've got more digits than that. We're showing 5 or 6 digits. You look at your problems, you're using 5 or 6 digits on them. So I'm just using, and I'm just, on those, I'm multiplying by a whole number. So we're still using a lot of digits. Okay. We don't have a whole number ratio. We know atoms go together according to Dalton's law, that they've got to go together in whole numbers, and we're not showing whole numbers, and we have to show whole numbers. So does anybody have a suggestion how I could keep that ratio, basically 1.6 to 0.8 to 2.4, that ratio, and make it a whole number ratio? Any suggestions? I could multiply, but that's going to, that's going to be tough to do. Figure out what number I need to multiply by. What I'm going to do is I'm going to take and divide by the smallest of the moles. And when I divide by the smallest of the moles, at least I know I get one whole number, right? So if I take this 0.7923 and divide it into itself, what do I get? 1. So I get 1 mole of sulfur. Now if I did, like in math, you do it one place, you do it all over the place, right? You do it on both sides of the equation. So we're going to do all of them by 0.7923, and let's see if we get whole numbers out. So go ahead and do the other 2 and see what you get. See if you get whole numbers for the other 2. Okay, so the formula would be Na2SO3, because we get 1 to 2 to 3 ratio. Is there an SO3 on there?
Yeah.
Okay, what charge is it?
-2.
-2. What's sodium? +1, right? Well, it works out that way too. Charges work out. So we're kind of just solidifying it when we do. If it's ionic, we can kind of look at that and do that. So for tomorrow, or for Monday, do those 2 problems in your homework, and I'll do the same as I did today. Come around and look at them. Okay? I'll rewrite them on here as well. The last step is the most important, and that's the one that's missed most often. You get students, they get those moles out there, and then they just automatically want to start rounding, and you got to do one more step, and that is the most critical step that students miss. They do not want to divide by the smallest whole number, and that just makes sense. You have to do that. Now, Monday, when we're going to do some that they don't come out to be whole numbers, and they'll come out. Some of them will come out whole numbers, some of them won't, and then we'll have to do one extra step, and that's not that huge of a step to do that. We'll do on Monday. We'll do one problem on that, and then I'll prep you for the lab. We'll do on Tuesday, and then Tuesday the lab will take the whole 50 minutes. There's a lot of time where you have to let things cool and weigh, and then heat them up and cool and weigh, and so there's a lot of kind of waiting and that, but if you do it right, you get some good numbers, and it should work out